Okay. So hello everyone. My name is Eric Schneider. I am a technical marketing engineer at Allegro AI, and today joins me Dr. Ariel Bieler, who's our evangelist. And today we're going to discuss superhero team up, data scientists and data engineers, basically bridging the gaps between data scientists and data engineers, and how can they both um, enjoy and improve their workflow. So today's agenda, we're first we're going to basically define the role of data scientists, data engineers, and talk about the friction point between them. Then we're going to kind of dive deeper into data lifecycle, model lifecycle, research pipelines, and then we're going to discuss Allegro platform a bit more and discuss about visibility features and orchestration. Cool. So let's begin. Just a short intro about Allegro. We were founded in 2016. We have our main product is called Allegro Trains, or now it's being renamed to ClearML. It's an open source, free experiment management and orchestration MLOps platform. We also have an enterprise offering and then a SaaS, a free SaaS solution. The product is being used by lots of big names that you probably know. You can read more about it on our website. And then let's go. Okay, so first let's basically define the differences between data scientists and data engineers. So if we start with the data scientist, the nature of the work is rapid iterations. Let me just pull up the spoiler alert. How do I do that? Okay, cool. Whoops. Okay, so, oh no, I did not want to annotate. I wanted to have a pointer. Whoops. So, okay, whoops. Okay, so data scientists, since the nature of the work is rapid iterations, basically, they're trying multiple hypotheses, they're trying multiple models, different train test split, different data sets, and so on. So they're more inclined to write quick and dirty code. You want to try that, you want to try that, you want to try that. You don't have time to write a robust code, but you want to try multiple things as fast as possible. Now, this also dictates that you also need multiple environments because different Python packages, different Python versions, sometimes they take off-the-shelf code that have all sorts of requirements, and this requires multiple environments. When we look at the data engineers, they get the model or they start working either when it's stable production ready code, meaning the model is already ready and we want to deploy it, or there is some sort of data cleaning, data processing pipeline before that. This means that it's also because their job is maybe more I don't want to say defined, but it's more methodical and semi-linear work. It's a bit more processed. You don't try this, try that. So then you don't really need multiple environments and you have an organized development environment. Basically, you know what you want, what's in, what's out, and they just need to get this done. And the data scientist has a best model approach, meaning they just want to get the best model possible, while data engineers tries to get a stable model deployment or stable environment to really do his job best. So there's kind of different needs and different characteristics to the roles and the work of data scientists versus data engineers. Now, also, the tech stack is different. If the data scientists have multiple tools, if they're doing deep learning, they're probably doing PyTorch or TensorFlow. If they're doing traditional machine learning, they do scikit-learn or XGBoost or CatBoost or whatever it is. And a lot of the time, because they want to run experiments, they're running Jupyter Notebooks or Google Colabs, so they can visualize very, very easily their work and maybe change something and rerun a cell. while on the data engineer part, it's PyCharm for Python and basically Apache Airflow. So there's different tooling between these two personas, and of course it causes friction. Now, friction points are data handover, when we basically move data from the data engineer to the data scientist part, data lifecycle management, meaning how do I manage the flow of data in the system and between the two personas, the different tech stacks that we just discussed about, limited observability, meaning both sides don't really know what each other is doing in real time or don't have the observability into each other's work. Moving, obviously, data science code or data science models to production. And then last but not least, resource management, meaning how do I manage my available resource, which is basically the compute, and making sure that everything that is available to me, I can see it. I don't have to like send an email or yell over the cubicle, hey, is this machine or is this CPU available for me? And basically just being able to utilize the available machines whenever possible. So, okay, so we have that, and let's now discuss a bit about data lifecycle or model lifecycle, obviously accompanied by a meme. So if we look at the model lifecycle, and this can be also called data lifecycle, they're kind of intertwined with each other. So the data engineer part, just get the point out. So the data engineer part is the green part. So first you gather the data, then you clean the data, and then you prepare the data and conform it so it's prepared for ingestion by the data science. Now, the data scientists normalize the data, they explore the data, and then they debias the data. And the exploration is very important because you want to know what you have, what you don't have, and maybe theorize about what you might further need. Then you train the model on the data, evaluate the model, and then move it to a third persona, which can be either the data engineer or an ML engineer for deployment and production monitoring. Now, everything kind of looks nice and lovely, but in real life, this is more complex. And the complexity comes from the data science nature of things. Now, if we look at that, we see that this is not a linear workflow. What happens is that model training and model evaluation happens once, happens twice. Actually, it's an ongoing and an iterative process, as I've said before. You have a model, you try it, it doesn't work, then you change your parameters or try another model and it doesn't work, or it does work and there's a gradual improvement, and then you try different data debiasing or different data balancing, different data slicing or mixing, or I'm trying to mix two data sets together, and maybe I'm doing hyperparameter tuning, which meaning that I'm running multiple experiments concurrently. And this job is really non-linear. And because this job is non-linear, it reflects back to the data engineer. Because if the data scientist found out that he doesn't have enough of a certain class, or maybe some data was not cleaned properly, and thus the model isn't performing as well as we wanted to, or there is any conclusion that maybe reflect on the data engineer. So there is a kind of a ping pong effect between the data engineer and the data scientist, where the data scientist kind of asks the data engineer to modify, and the data engineer returns it, and there's kind of this negotiation. Now, this negotiation, unless it's managed properly and you have an overview of this whole exchange, which is inevitable, it's not going to run smoothly. And this is a very, very big friction point that we identify between these two roles. Now, if we look at the data lifecycle from the solution point of view, meaning from the data lifecycle friction points and the solution. So first we have a convention disparity, meaning both might not use the same language. Maybe one label would be cat with the capital C and one with regular C. or stuff like that. And the solution for that is actually to use a single platform. And we'll see the thread of using a platform that kind of forces us to work organized in a way all throughout this webinar. But what the platform does is basically conform stuff for us, and also gives us visibility into each other work, and visibility 100% helps prevent or reduce such mistakes. So there's that. There's the code modification and handover, meaning we don't want to modify the code whenever it's not necessary. We don't want to change a parameter and then do git commit and then rerun our experiment, because our git log will become endless and untrackable. And we don't want to modify code because it's very, very error prone. Also, we don't want to manually hand over, okay, this is the SQL query, oh, this is the git hash, you can run this and see the problem. We want to have stuff modified from the UI, and we want to modify only the parameters. We want to have like a certain set of parameters, and for a given model or a given script, we want to just change them. So that's a way to eliminate code modification and reduce handover, manual handover. Now you have manual data movement, because when you have multiple training machines, you need to move the data to each machine, and you don't want to manually do that. You also want to avoid duplication, because what happens a lot of the time, if you want a subset of your data, what you'll do is you'll basically copy paste your entire data set, remove all the frames or data points that you don't want, and then retrain. And this causes data duplication, and we don't want that. And the solution that we provide or suggest is using hyper data set. So using hyper dataset, basically you can tell your code what version of the dataset you want. We also version the data on top of everything. And then basically we say, okay, I want just this subset of the data, and the hyper dataset is in charge of giving you the data and not duplicating, meaning you have a certain central data storage, maybe an S3 bucket or a network attached storage or something like that. And then it fetches only the data needed automatically. You just need to query it, and then you get the data needed. Now, in order to query it, you need to index everything. And this answers the problem of hard to manage unstructured data. We basically want to make unstructured data behave kind of like structured data, and then we can query it, we can get subsets of it, we can mix two different data sets and pipe it into one experiment. And this is very, very useful. And of course, everything is done with a configuration and without changing the code and without writing custom code for each data set. And this kind of discuss about data slicing and debiasing requires custom code, and mixing and matching data set is difficult in the manual. And again, indexing the data and the platform takes care of conforming really, and it all goes back to using hyper dataset, which basically index your data and gives you only the stuff that you ask for. And I'll show you the whole concept in a bit when we do the demo, and it'll be much easier to understand. And there was a really crazy thunder just right now, so enjoy the stormy weather. Okay, cool. So this is the ideal. We want data scientists and data engineers work together, and what does it is data management or data lifecycle solution. Cool. So this is kind of how it looks at Allegro, at our platform. As you have here on the top left corner, so you have the data set versions. You can have multiple different versions, meaning let's say train and tests, and you can have multiple versions of each one. We have here some basic statistics on the data, and then you have thumbnails so you can preview the data. This is how a single data point looks. We have the raw image, we have the annotations, and we can see the annotations on the image, and we can also have some metadata on these images or this image. And this is how we tie it into the experiment manager, which I'll discuss briefly. But here, basically, I'm telling what do I want to get? Meaning, now I tell that I want to get it from Pascal dataset, and I want to get a bird, and I want to get a cat, and I want to get a cow, and I want the ratio to be 1 to 1 to 1. And I didn't have to write almost a single line of code for that to be done. And obviously, I didn't have to rewrite it into every new repository, every new script that I did. And I'll show you how we tie it into our experiment management solution in a second. Cool. So okay, cool. So experiment management, and this is based mainly geared towards data science, but what we want to achieve here is completely reproducible and completely documented research workflow. And this means everything from data to parameters to code to environment to everything. Now, if we look at the ML research workflow, what we hear a lot of the time is that you get a data set and then you train on the data set and then you validate. Maybe you train multiple times with different configurations and then you validate multiple times. Then you have a model that you get, and then you just put it in a hub and or feature store or whatever, and then it's up to the ML engineer or data engineer to basically serve it. This is very linear, very simple procedure, and looks quite neat. But in real life, this is kind of how it looks. Because every step of the way, there are multiple factors that you need to take into account. Plus, you need to remember that this is an iterative process and not a linear process. And train and validation and get data sets actually happen multiple times. And you need to basically, you need to log everything. You need to log the parameters and the label you use and the uncommitted changes, because you don't want to do git commit every time. And you want to the system environment and resource management and all the artifacts that you got, and then the pre-processing pipeline that got you actually the process. And it's really a lot of work. A lot of people do it manually, maybe use an Excel file, maybe other method, maybe write on their own. But there comes a point, and nowadays it's very, very soon in the research pipeline or workflow, that you really have to use a platform. Otherwise, your work is not reproducible and you're kind of losing your arms and legs over there. So our solution is basically to put automatically or automatically captures everything. Yeah, you see here that we capture the source code, the repository and commit ID, and the script that you ran. If you had uncommitted changes, we also save those. And the environment, so later on we can reproduce the environment. All the metrics that came out of it, including monitoring of your machine, which really helps with debugging. And yeah, this is basically a short overview of that. I'll go over this into a bit more details when we do the demo. Cool. So now I want to discuss about ML pipelines and how do we utilize them and why they're so important. So ML pipelines such as this one are fairly standard in data ingestion and deployment, which is the part that data engineers or ML engineers are in charge of, but they're heavily underutilized in research. Now, if we look at this plane of interface versus specificity, we see here two extremes. So on the top bottom axis, we have automagical, which means it just works. And on the bottom part, there is the expert only part, which basically means that you really need an expertise or someone who's very familiar with the product or the code to run it. And on the left-right axis, we have flexible, which is basically I can mix and match data, mix and match code, mix and match version models, whatever. and very specific use case, meaning it's geared towards only a single use case. Now, research, because of the iterative nature, wants to be as flexible as possible, meaning that I don't have an overhead or it doesn't incur any penalty to really change from one model to another, from one data set to another, and so on. But usually, because of the flexibility, it's for experts only, meaning you can't just drop down a data scientist, tell him, okay, this is the code base, go wild. You need an expertise. You need a lot of training. You need some handover between team members and so on. It doesn't explain itself, and it doesn't just work. On the other end of it, there's production. Production, you always want to just work, and this is one of the main goals of moving research to make it actually business worthy or business ready. You want to productionize it, and you want to make it automagical and make it just work. But it's usually specific use case. You don't change models every day. You have your model, it works, and it loses on the flexibility. Now, the prototype comes kind of in between. We're taking research, we're modifying it. It's not final, so we still retain some of the flexibility, but we lose a part of it, and it kind of works better, and it's closer to production. But you see, there is a very, very big gap between research and production. Now, if we want to think about an analog, we can think about coffee. So on the left, we can see coffee as an art, and this is how the data scientist kind of captures the world. So coffee as an art is meaning that, I don't know, I'm grinding my coffee in a different way every time. I'm kind of weighing it, but maybe there's a bit more or a bit less. The temperature isn't uniform. So every cup of coffee is very, very good and very unique, but you cannot reproduce it. No two cups of coffee are alike. On the other end of it is that just works. You have a coffee machine, you press a button, and you drink this very mediocre caffeine rush liquid, which is okay, but it's not amazing. Now, we want to kind of move the art into the realm of just works. And this is where research pipelines are meant to be. So if we, this is where pipelines are bringing research to be. So research was here, and if we use pipeline research, it's kind of here, because we definitely lose some of the flexibility, because when there is a pipeline, we cannot just interchange stuff in the middle or links in the chain very, very easily. But it's much easier to run it. I can just basically spin up a machine, install the environment, and I can run the entire pipeline on the machine. And basically brings our research from here to here, and the gap between research and production is much narrower. Now, also, you get a lot of benefits of reproducibility, and you get the benefit of data engineers and data scientists who are using the same tools. So it's very, very, very useful in bringing the data scientist kind of closer to the data engineer. Okay. So how Allegro imagines pipelines should be. Now, pipelines should be as easy as this code snippet. So you have your pipeline object, and then you have an add step. You give a name of the step. You give a name for your step. You give the parent, meaning when should it run, when it should be executed. You give a base task name, a base task project. Tasks are basically experiments in the Allegro system, and you give it a task prototype. You can think about it as basically as a code version, or which code should I run, and then what parameters do we override in this code, And then we add multiple steps, and then we run pipe start, pipe wait for finish, and pipe stop, and that's it. As simple as that. And because it's so simple, it's very easy for the data scientist to add it to their workflow. It doesn't incur too much of an overhead, but it helps to greatly organize the workflow. Now, I said pipeline, and everyone thought, okay, but what about Airflow? Because Airflow is our pipelining solution. Now, Airflow is a great tool. We're not trying to replace Airflow. What we're trying to say here is that Airflow incurs very large overhead for data scientists. And because of this overhead, there's kind of a technical debt that they incur. And they're, okay, yeah, I know that using Airflow would be good for me, but I'm not sure it's really worth it. And because Allegro pipelines are so much simpler to start, then data scientists can start using our pipelines, and then moving to production, we'll wrap these pipelines with an Airflow wrapper and then take it to production. So you kind of enjoy the best of both worlds. You enjoy the simplicity of Allegro pipelines and the Swiss Army knife or robustness or usefulness of Airflow, and you don't throw away all your current pipelines. It basically integrates with your current pipelines. Cool. So this is how pipelines work in Allegro. You see every node of this is a task. These are the artifacts that go between one task to another. And you can see the status. So this task passed, this task failed, and we can see that this is not going to progress because one of the tasks failed. Okay, coming to an end, we'll talk about a bit about ML orchestration. So ML orchestration, or as the new hot buzzword MLOps, it's basically how we see it is, how do we first scale experiments? I have experiments on my local machine or on my on-prem GPU machine, maybe an NVIDIA GTX or something like that. And how do I take that and scale it to the cloud very, very easily without, again, manually SSHing into each machine, Git cloning the code, SCP data, and so on. So how do we do everything automatically? How do we leverage other people's work? A bit of pipelining and automation. How do I make sure that maybe each part of the pipeline runs on a different machine, and then we aggregate it automatically? And then lastly, how do I know what is running and what is running where and what is currently available for me? So when we talk about ML orchestration, this is kind of how we talk about, how we think. It's less, or we're not dealing as much with the deployment part of the orchestration. Another useful features are visibility features. And visibility features really help understand what each party is doing and maybe get a bit more intimate with your workflow or with your experimentation. So we have data visualization features. We have a visual search engine for on-the-fly dataset creation, meaning I can say, okay, show me all the images with cats and dogs and cows or something like that. Now, the visibility features also allows data engineers and other stakeholders get a kind of a glimpse into the data scientist's work, and then really understand what is the data scientist currently working on, what are his struggles, what's working, what's not working, and so on. And then you also get an overview of your machine utilization and expected workload, which we've discussed in the orchestration part. Cool. So that was the I don't know, artsy part or the theoretical part of it. Now let's do a very quick demo. Cool. So our platform looks like that. It has basically, let's call it 3 pillars. It has the experiment management, data management, and then orchestration or MLOps. Now, in the experiment management, we have multiple projects, and each project has multiple experiments. And as as I've shown before, we save everything from your source code to uncommitted changes, to install packages, to the base Docker that you used. We save all the configuration, and later we can override them. We save the artifacts, basically input model, output model, and everything that was a byproduct of your experiment. Let me just do full screen, I think, be nicer. Then data view, and data view is the hyper data set that we've discussed. And over here, I can choose the data set. I can have filtering. I want only specific images like bird and cat and cow and dog. And I want the ratio very specifically. And then I want to do mapping or conforming between 2 data sets. I want to choose the label enumeration, and I can also choose an augmentation pipeline if I want to. And lastly, I have the full logs, full stdout logs. All my metrics, including the machine monitoring metrics. And then I have here also visual representation of what the actual network is inferring, and I can also do it with audio and HTML and so on. Another useful feature is the compare dashboard, where I can compare inputs. For instance, let me go to configuration. Cool, so I have different LR. I could have done it here probably. And then I have different batch size and different test size. And then I can see, okay, cool. Now I can see that the green model is behaving or performing a bit better than the brown model, and then I can theorize about why it's happening and so on and so forth. So this is very, very useful. We have the data set management, and then this is, as I've shown you, we have here data versioning, multiple data versions. And then I have here some basic statistics on my data, which is basically the label distribution. And then I can go into frames, and I can see the labels on the annotations. I can scroll through it. Very, very simple. I can see some metadata on the frame. And so it's very, very useful. And as I've shown you before, the hyper data set kind of ties in the data management part and the experiment management part. I also can, let me just change that. I can also search my data set. So let's say I have a cat. No, here's a pedestrian, I think. Right. On an image with a pedestrian. And then I want something like car. And I want a cyclist. So now I have all the frames, which is 284 out of 7.5K, which have pedestrian, car, and cyclist. And I can also have a frame rule, which is something like height or width or anything like I want to, if I have a metadata on where it was taken or time of day or speed of the car, so I can do much more complex queries on my data. So this gets me to explore my data much better, but everything that I can do here, I can also do in the experiment management. Now, if we talk about pipelines, this is how pipelines look in the real world. We have one task, second task, third task. And then I have here each stage of the process. I have the task ID, like what did it actually ran, and what were the parameters that we've overridden. So it's very, very handy and useful. I can also play with it if I want to. This is a very, very simple pipeline, but you can create much more complex pipelines as you wish. And lastly, this is the MLOps part. If I want, I have the machine monitoring. It's like a dashboard. This is basically the available workers or available machines for me. Currently, I see that I have here 3 available machines. And maybe if I go into one of the machines, I can see that in the last 1 day, the GPU usage was, I had a few spikes. Maybe I can look at the memory usage, and I can really analyze my work. Now I can also tie in the experiment management solution into this, and I can say, okay, please, if I go back to the experiment management, so I can ask him, okay, please take this experiment and run it on this machine. And I can modify my parameters and data and so on and so forth. So this is really handy that all three, experiment management, data management, and orchestration solution, are being handled in a single platform. Okay, this was a very, very, very quick demo. You can see more on our website, or you can just try it out for yourself. And coming back, let's sum it up. So as we've seen, data scientists and data engineers have different needs, and those needs should and need to be breached in order to make everyone's work more efficient and basically foster closer collaboration between the two entities. Allegro provides an integrated experiment management, data lifecycle solution, and an orchestration solution, which all tie in together very, very neatly. I don't know if you can see this flickering, but I definitely can see it flickering. Let me move it. I don't know what's going on. Cool. Data lifecycle management provides a single control plane for data engineers and data scientists to manage data. And this is really helpful because when the two parties really work on a single control plane, it smooths workflows immensely. Bringing research close to production using research pipeline is invaluable, and an MLOps solution or an orchestration solution provides an overview of our organization's machine and allows you to tie in experiments into resources. Cool. So what do you need to get started? So you can clone our code from GitHub. It's completely open source, at least part of the platform, the experiment management and the orchestration solution. If you have any questions, join our Slack channel or follow us on YouTube, where we release multiple videos and tutorials. Check out the webinar that we've done about getting started with Allegro trains. And then you can also check out our blog post and obviously review the documentation. If you have any question, most likely it's there. Another thing I wanna talk about is which will be the last thing, is how do I actually start working? Okay, I've cloned your code. I've registered into your SaaS, or I've created my own server. So how do I start? First, you integrate our SDK into your own code, which usually is just 2 lines of code. You import trains, and then you just do trains init or task init. Then you create your server. Currently, we have a SaaS solution at clear.ml. You can find more information about it, which will basically be your server, but you can also create your own server or use our test server or demo app. And then basically you run your experiments and basically, you run your experiments and they report to the server and you can start using it. So first stage, integrate our SDK, pip install trains, and then integrate our library. Then create your server, choose the server of choice, and configure, tie in your SDK to the server, and from then on, you're good to go. So yeah, thank you very, very much for joining me in this webinar. I hope you enjoyed it, and hopefully you learned a thing or two. If you have any questions, don't hesitate to ask on our Slack channel, open a GitHub issue, whatever works for you. And yeah, thanks again.